Unit 6, Lesson 2, Algorithm Efficiency. To conclude this lesson, you will be able to use linear search to determine if a number is in a list, use binary search to determine if a number is in a list, and compare the efficiency of linear search and binary search. First, have you ever lost a pencil in a backpack? What are the steps that you take to find it? Do you just dump the whole thing upside down? Scrounge around? What do you do? Well, maybe you use a systematic approach. You search through every pocket in order. Start from the outside, work in, maybe start from the left or the right, whatever. Or maybe it's just random approach. You just stick your hand into any pocket and just start grabbing. Some of you may have a system where you place your books and materials in your backpack to be retrieved in the order of your class schedule. If you look in your bag at a certain spot and don't see the pencil, you have a pretty good idea where to search next. There are no right answers here. The idea is to start thinking about the efficiency of different search methods. Now, we're only going to look at two different searches, linear and binary. There are a number of different searches out there. These are the two which we will focus on. If you go on and you take Computer Science A, you'll do a lot more. Now, I need 3 volunteers in class. And what you'll do is you're going to navigate to the second level of Code Studio, Unit 6, Lesson 2, Level 2. And there's a ticket generator. You're going to click to generate your raffle ticket number. Then you're going to write the number on a sticky note or a scrap piece of paper. And if we're in class, you come to the front of the room. If we're virtual, you're going to be prepared to tell me your number when asked. Via virtual, it'll be a chat. Okay? Now, the problem is, figure out if anyone has the winning raffle ticket. Instance, a list of tickets plus the winning number. Let's check to see if anyone has the winning number. Now, obviously, I can't do that. If you've got the winning number, you've got a ticket, you generated a number, or pick a number. Let's see. Did you have the winning ticket? 816? Great. If you did, that's great. If you didn't, it's okay. We still had to check once, right? That's how we searched. Well, how many steps did it take to find out if anyone had the winning ticket? What is the greatest possible number of steps it could take for this instance? Think about that. Well, if you think about it, if I had 4 tickets, I could potentially have to check all 4 tickets. Okay, that's the greatest number of things I would have to check. If we had 6 volunteers, 6 different tickets, how many tickets at most would I have to check for a winning ticket? 6. The whole school, however many were in the school. The pattern here, what is the pattern? Hopefully notice that the pattern is a one-to-one relationship. The number of tickets in the raffle exactly equals the number of steps it would take to check for a number in the worst case. Well, worst case is linear. It's y equals x. If I have 3 inputs, I'm going to need 3 steps. I got to check it 3 times. If I have 6 different things, I'm going to have to check all 6 before I can rule out that it is or is not in the list. 10 goes to 10, 100 to 100, and so on. Every time I add another ticket, it adds another step. Now, do this. Use the ticket generator to generate 7 tickets, or 7 numbers. Okay? Write the numbers down on separate slips of paper. Organize the papers in numerical order, and then copy one of the numbers onto a separate paper. This is the number you're searching for. I have my examples here. You can use different examples. Okay, so I've got them here. I'm going to look for 705. Now, the challenge that you have is to create an algorithm to determine if a given number is in a list of sorted numbers. If it's not, you can say it's not in the list. But the search can start at any of the numbers in the list. It can jump over numbers. In other words, you don't need to search the number in order. You can determine which numbers to search next based on the current number you're checking. The goal is to make the determination in the least steps possible. But don't forget, your number could be anywhere in the list. What is the worst possible case? What is the greatest number of comparison steps it would take to find any number in your list? using your current algorithm. Okay, remember, you're going to use your algorithm. You're going to come up with an algorithm to search through this list, any order, any way, but it's got to be directions. It's not, I just see it. That's different. If you tell somebody all these are turned upside down, how would you go about doing it? Okay, pause the video and try to come up with your algorithm. Go. Okay, now share and compare. With a partner in class, you'd be asked to share your algorithm. Try your algorithm, try their algorithm. Run through both fully. Determine which one's faster and which one takes the least amount of comparison steps. Virtually, we would do it in breakout rooms. In class, we do it all together. Right? Now, what I want you to do is to try this. I want you to run through this, look through this, compare it to your own algorithm. Okay? Find the middle number in the list, compare that number to the given number. If it's found, you're done, jump it out. Otherwise, if the number is less than the given number, remove all the cards to the right, including that middle number. Else, the number is more than the given number, remove all the cards to the left, including the middle number. Then find the middle number in the shorted list and go back up and repeat until either there's nothing left in the list, in which case your number is not in the list, or you found it. Pause the video and try working through this one. Okay, this is what we call the binary search. Let's do this. I'm looking for 705. So I look at 117, 232, 245, 410, 705, 716, 833. I'm going to look at the middle one, and I'm going to compare it. And notice that 705 is greater than 410. So I'm going to get rid of everything to the left, and I'm going to look up here. I'm going to find the middle one, and I'm going to compare it. So when I compare 705 to 716, I find the 705 is less than. So I'm going to get rid of everything to the right. Now, I'm going to compare 705 to my small list, which is only one big, and guess what? It's equal to it, and hooray, I found it. It took me 3 tries. Now, try the binary search algorithm for different instances. We've done a few for you. I've done a few for you. Copy the instance table into your notes, your journal, and plot the points on the graph. If you have one item, well, it's only one. If you have 3, you're going to check the middle. If it's not the middle, you got to check the left or right, so that would be 2. If you have 5 items, okay, oops, let me get myself a pen here. If you have 5 items, 1, 2, 3, 4, 5, you're going to check this one. If that's not it, now you're going to check the middle of these 2, which doesn't matter. You're going to check this one and this one. So you might have to check 3. Okay, but what about 7? Well, guess what? If you have 7, you still only have to, at most, do 3 checks. Why? 1, 2, 3, 4, 5, 6, 7. Well, I'm going to check this one. And if it's more, then that means I get rid of all of these, and I'm left with these 3. I'll check this middle one. And if it's not to the right, I get rid of these, and this is either what I'm looking for, or it's not, but it's still just 3 checks. What about 9? Well, 9, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I check here. It's less than. So now I've got to make a decision. This one or this one. Doesn't really matter. If I check this guy and I say, oh, it's not more than, I have to come down here. I check this guy. It's not him. I check this guy. 1, 2, 3. I had to make 4 checks. Okay, 15, still just 4 checks. Try it. Okay? Because remember that when you eliminate half of the list, you're getting rid of more than just one because your list is in order. Because your list is in order, you can just, if it's something's more than or less than, you can wipe out everything above or below. Now, another way to think about this, can you see a pattern here? If I have one input, I need one step. How many bits does it take to represent 1 in binary? Ooh, 1. What about 7 in binary? I need 3 bits. Ah, look at that. Takes 3. Okay. Also takes 3 here. What about 9? It takes 4. Do you notice? However many bits I need to represent the number, that's how many times I have to check it. Okay, or that's the maximum number of steps. So however many, whatever my number is, the number of bits to represent that number is how many steps in the binary search at worst case to determine if it's in the list or not. So here's our 2 search algorithms. The first is linear. As we added more inputs, the number of steps grows at the same rate. I add one, I add a step. I add another step. The second represents what happens with binary search. Notice how it grows at a much slower rate. It still grows, but not as fast. Binary search is faster than linear search, but the data must be sorted first. So it kind of depends. Yes, with 3 items, it could take me 3 checks, but you know what? To sort the 3 items might take, and then to find something that's not in the list, the trade-off might not be there. Or if you're only going to search for something once, maybe you don't want to spend the time sorting it. But if you're going to look through a list often, have it sorted, and the binary search is your fastest way to go that we know of right now. There are some other searches that are faster. We're not going to get into those. As a wrap-up, if I had one input, which algorithm would I use to get my answer with the fewest amount of steps? Well, if I had one input, I'd just use linear. It's the easiest one. I don't have to figure out a middle one. Just boom, done. What if I had 5? Well, it depends. If I'm only going to look through this list once, if I only have to find something once, I'm probably just going to do a linear search. But if I start going to 100 or more, and especially if I'm going to be looking more than once for something in the list, I'm probably going to sort the list and then use binary. Binary would be faster. Efficiency is a measure of how many steps are needed to complete an algorithm. A linear search is a search algorithm which checks each element of a list in order until the desired value is found or all the elements in the list have been checked. A binary search is a search algorithm that starts in the middle of a sorted list. Very important. It has to be sorted. Numbers and removes all of the data, either to the left or to the right. So it's going to remove half of it. This process repeats until the desired value is found or all the elements have been eliminated. Binary search is faster than linear search, but it can only be done on a sorted list. Well, I shouldn't say it can only be done. It only works properly all the time on a sorted list. All right, so that's great. Well done. It's clear that there are many algorithms that we can use to search for an item in a list. Some are faster or more efficient than others. In the case of binary search, the larger the list we are searching through, the greater the efficiency in using this algorithm instead of the linear search.